Today's lecture focuses on filtration design. We'll focus today on the hydraulics of filtration.
Talking about, in this case, granular media filtration. So we're talking about a passing water been treated typically through some sort of screening followed by treatment, either softening or coagulation, sedimentation, and now we're looking at removing those particles that were too small to be removed by sedimentation. So in order to design this, we need to understand something about the media. Basically, all of filter design is really based on hydraulics. So if you didn't like chemistry, don't worry, we're not going to do much chemistry in this unit. It is all hydraulics. If you don't like hydraulics and chemistry, I'm sorry. It's what it is. Okay, so what I've given you here is the data from two different companies, and I've set this up as they're vying for a contract to provide filter sand. So this is actual data obtained online, two different companies, one from Flint, Red Flint, and the other from Northern Filter. And they've provided this information, okay, where this is the cumulative mass passing a sieve. So those of you that have done sieve analysis in 312 or 337, this is essentially the same thing we're doing here. Just not using it for aggregate, we're using it for filter media. So you can see here we've got mesh sizes, we've got sieve openings, and then, so for instance, with the Red Flint one, 87% of the mass of sand would pass through a sieve with an opening of 1.18 millimeters. I have a video going through explaining sieve analysis, showing you how it's done.
However, in the interest of time, I won't show it now, but you can watch it later.
So what I've done is I've taken the data from the previous slides and I've plotted it as the percent passing versus the particle diameter, or really the sieve size opening. Okay. And I've done that for Red Flint 1, which is in blue. So here we've got Red Flint 1. We've got the Northern Filter. And then the green is Red Flint. Okay. I've also added lines on here for 60% and 10%. Okay. And the reason that I've done that is that we defined two terms that we use extensively in filter design. And one is the effective size, and that is referred to as P10. So it's the size of the particles for which 10% are retained. So here, so, or 10% pass, okay? The reason this is important is that this tends to control head loss. And when we go through the calculations shortly, you're going to see that it's the smallest size that will control the head loss, that will exert the greatest head loss through the filter. Okay. And then the P60 divided by P10 is equal to the uniformity coefficient. So both of those are important in terms of the design of these filter units. So to determine the effective size, as I've just mentioned, this is P10. Okay, and then the uniformity coefficient is P60 over P10. Okay, and I'm just gonna, the interest of time, you can read this off the graph. Red Flint 1 is 0.7, Northern Flint is 0.5, and Red Flint 2 is 0.44. And typically we want these to be in a range, and I don't have that written down, about 0.4 to about 0.7. So all of these are within the range. And then the uniformity coefficients, and I'm just gonna, this is P10 or E. Then the uniformity coefficients are for Red Flint 1 is 0.97 over 0.7, and that is 1.39. 0.65 over 0.5, and that's 1.3, and I'm just reading these off the graph. And 0.6 over 0.44, and this is 1.36, and we want this between 1.3 and 1.8. So all of these fall within the range. So in terms of usage, we could use any one of these for filter design. So they all meet the design. Effective size 0.3 to 0.6. I said 0.7, so it's 0.3 to 0.6, and then 1.3 to 1.8 for the uniformity coefficient. So this one's a little bit high. The others all meet the criteria. So we're going to pick the Northern Flint. The next thing we need to do is to determine the percent retained between the two sieves. I can go through this kind of this way. I can have you go through some of this in breakout rooms. What's most helpful? You can kind of do it as a regular lecture. It's basic, the whole thing is basically a giant spreadsheet. So I've got one lecture. We'll do it as a lecture, okay? So the next thing we need to do is to determine the percent retained between two sieves. We're now looking at between the two adjacent sieves. So when we do the sieve analysis, we have a series of sieves from the largest to the smallest. Okay. And here the percent retained is just 100 minus 99, 99 minus 98, and you're going to want to set up a spreadsheet like this for these problems. So 98 minus 9. So at this point, it's just simple subtraction. Now, so we're looking, notice here, so we're looking at that retained between two adjacent sieves. Okay, and as the mesh size, just if you're not used to this, as the mesh size increases, notice your sieve opening deep, and it's purely convention. The next thing we need to do is determine the geometric mean. So the geometric mean is just the product of D1 times D2 to the square root. So if we just go back and look here, our sieve openings are 1.18 and 1. So this is just 1.18 times 1. Take the square root of that, and that is 1.08. So do the same thing for the next set right here. And that is equal to 1 times 0.85, take the square root of that, and that is 0.922. So we're going to do that for each of the size fractions that we have here. And we now have the geometric mean of the two adjacent size sieves. Now, looking at the filter.
Quick question on that. Can you go back to the previous slide?
Sure.
So for 18, the geometric mean is the two numbers 16 and 18? Or is it for 18 and 20?
So for this one here, this here is equal to the square root of 1 times 1.18. This is equal to the square root, okay, of 1 times 0.85.
Thank you.
Okay. Now, so what we're designing is this filter. This is referred to as a filter cell, part of a filter box. Notice it's a cutaway here. And in the videos, I've provided you with videos, some of which I've shot, some of which I've gotten off the internet, showing you the filter design. Okay. During operation, we have a stagnant water layer above these water troughs. Okay, so we've got water. This whole thing is just filled with water. And water is just percolating down through the sand. We may have a mixture. So for instance, if we have single media, it's just sand. Dual media tends to be sand and anthracite. And multimedia tends to be sand, anthracite, and garnet. And the reason these are used are because they have different sizes. So anthracite tends to be larger than sand. It also has a lower specific gravity, so it's less dense. So during backwashing, it stratifies on the top. We want the larger particles of our media on the top and the smaller at the bottom. We want to use as much of the filter media as we possibly can for filtration. And so the water's flowing down through the sand, then through a graded gravel, then into perforated pipes. So these pipes are all perforated. And then is collected and moves on to the next process. So you can see it flows into here. Okay. Now, I'm going to change colors because that's during operation. During backwashing, the opposite happens. So during backwashing, now we have flow. So the red is backwashing. Now we have flow in the opposite direction. We have flow now up. We fluidize the sand. So basically the sand particles are essentially floating. Okay, so there's void space between these particles. We dislodge that material that's collected, and that water, so the backwash water, then flows into our water troughs, and then can be collected for further treatment or disposal, depending on the facility. Okay, so we operate during typical operation with a flow down, and we're using the static head to ensure that we have flow. If the filter sand gets clogged, what happens? So if the filter sand becomes clogged. Exactly. It doesn't filter. It doesn't flow. Same thing, just think about when you've done a filtration experiment. You do a filter experiment and material collects on the filter paper, and after a while, it doesn't filter. Okay. So what do we do at that point in time? So when we get to the point where the head loss exceeds some critical head loss, what do? We backwash. Exactly. These are too large to actually stir the sand, although we can agitate the sand with air to try and better dislodge material. And essentially, I guess we are stirring up the sand in this backwashing. So when fluidizing the material, we essentially are stirring up that sand. We're dislodging material, collects in the filter trough. So the two criteria that we use to determine when to backwash are critical head loss, exceedance, or turbidity. And we're required by law under the Safe Drinking Water Act to monitor the turbidity in the effluent. So in that water from here, so we're monitoring turbidity. If it exceeds a certain critical value, we backwash. Now, typically that information then is fed into models, experience, and we often backwash on time. So now this is automated, but we monitor head loss continuously. We monitor turbidity continuously. We backwash typically now on every 36 to 48 hours, but we can backwash more often if the head loss is critical head loss is exceeded or the critical turbidity is exceeded. This is only half of a filter box. There is a main trough, which is what you see right here, or gullet. And there is a mirror image of this unit on the other side. Okay, so always think your filter is always two of these. Okay, you will also never have one filter. You'll always have two filters, and that has to do with the hydraulics, because the hydraulics are complicated. So we always put in two filters. So you were told that the area of the filter is to be 25 to 100 square meters. And that is typical size for these filters. And you're told that the approach velocity for the standard rapid filter is to be less than, there's always an even number of filters. Okay. Filters and filter beds. Okay. So when we design these, typically what you'll see is a main pipe coming from the previous filter. Okay. You then have a pipe coming off that main pipe. So kind of in this way. We have one filter bed here, one filter bed here, and this has two cells. So this is cell one to the cell two of filter one. And then this is cell one here, cell one of filter two. You'll always have an even number. If two filters aren't sufficient, okay, you're going to then put in longer pipe, and then you'll put, and I'm running out of space over here, but this will be filter 3, filter for both of which have 2 cells. Okay, does that help? So what you're asked here is to determine the minimum number of filters required. So you're told that V sub A, which is our approach velocity or filtration rate, and that has to be equal to or less than 7.5 meters per hour, typical units that are given. So Q is equal to 0.2 meters cubed per second times 3,600 seconds per hour. We'll divide that by the approach velocity or the filtration rate, and that equals 96 meters squared. So this gives us the area. So how many filters do we need? Has to be within 25 to 100 square meters. Exactly, 2 at least, okay? And the reason we need 2, one is the hydraulics, but the other thing is we need to be able to meet the demand and treat at the maximum daily flow rate with 1 filter at a service for backwashing. When we backwash, we're backwashing the entire filter. So we don't backwash just a cell. So it's divided into 2 cells, but the whole thing is the filter. And we backwash the entire filter.
Good question.
Mm-hmm.
Why is the area of the filter given as a range between 25 and 100? Is that just, those are like the options that are available?
Those are typical sizes. So typically these filters are constructed on, they're concrete. They're constructed on site, and the typical sizes are between 25 and 100 square meters.
So if the required amount was, say, 50 instead of 96, the answer would still be 2 because you'd use 225.
Say that one again.
If the required area was 50 meters squared, you could use 2 25 meters squared filters for a total of 50. Does that make sense?
As long as we didn't okay, so good question. Let's just look at that. And so if we take 2, let's see, it's 720 cubic meters per hour, right? If we divide that by 50 square meters, we only have 1 filter, okay? So if we say that we only have 1 filter because the other filter is out of service, what is our approach velocity? It's 14.4 meters per hour. Okay. So that exceeds the 7.5 meters per hour. So if we put in a filter, okay, that was only 50 meters squared, we can't meet the demand with 1 filter out of service for backwashing. 2 is absolutely the minimum because of backwashing, because we have to backwash regularly. We're backwashing typically somewhere between typically 36 to 48 hours. Can be more often depending on how effective sedimentation is. Does that help? So where does the backwashing water go after the process? It depends on the process itself. For groundwater, exactly, you treat it again. Surface water is different, okay? Surface water is more complicated. because of the potential for bacteria in that water, it may very well just go to the sewer. Okay, groundwater, typically that backwash water, if it is a groundwater system, okay, that if it is a groundwater system that is not under the influence of surface water. So City of Lansing is such. Groundwater is pumped, it's pumped to the plant, and that water never sees the light of day. Because of that, the potential for bacterial contamination during processing is very small. So there, they do recycle that backwash water and retreat it. It gets treated again and again and again and again. Now the question is about never-ending loop of particle buildup. The reason that doesn't happen is because of sedimentation. You're giving those particles another chance to settle in the sedimentation basin. If it weren't for that, you're absolutely right. There would be the potential for particle buildup. But sedimentation gives that second chance. Okay, so we've determined that, so once we've determined the number of filters, okay, then we can calculate the approach velocity. So with 2 filters in operation, we've set got 2 filters here. So with 2 filters in operation, our approach velocity is 3.75 meters per hour, okay, or 90 meters per day. And this needs to be less than 180 meters per day. So we're fine. Okay. With 1 filter in operation, so we're backwashing the other filter. So we're treating all of the flow through, let's say filter 1. Our approach velocity is equal to 7.5 meters per hour. That's equal to 180 meters per day. So we're right at the limit. So this is based on 2 filters, and each one is 96 meters squared. So when you're doing your designs, 1, make sure you have an even number of filters, and make sure that you do not exceed this backwash, this approach velocity with 1 filter out of service for backwashing. Okay. Those are your major constraints. So think about that when you're actually doing the design. And we can also calculate this, and I'll do it here. We will use this for the design. We will need an approach velocity in meters per second. So I've just done the conversion there. Okay. The next set of calculations we're doing are to determine the Reynolds number for each size fraction. And that is equal to this particle shape factor. The particle shape factor would be 1 for a sphere. So if all of our particles were spherical, the particle shape factor would be 1. The more angular they are, the lower that value. Okay. We've calculated the geometric mean times the approach velocity divided by the kinematic viscosity. So this is equal to 0.75 times 1.0863 times 10 to the minus 3. Before we had the values in millimeters, make sure you convert to meters, times the approach velocity, and we will divide that by the kinematic viscosity at the temperature that you're given, and that is equal to 1.12. So we will do the same for all. Okay, so this here is just the 0.75 times 0.922 times 10 to the minus 3 meters times our approach velocity divided by the kinematic viscosity. Okay, and that is equal to this value right here. So we're going to do that for each. So that's why we want the spreadsheet. So that gives us the Reynolds number. The next thing we need to do is calculate the drag coefficient of drag. So we use the general equation. So that is simply here. So again, we're going to do the same thing. We've got coefficient of drag for that first particle size fraction. It's just 1.24 plus divided by 1.12 plus 3 divided by the square root of 1.12 plus 0.34, and this is 24.7. So that's that first fraction. We go down, 24 divided 0.948 plus 3 over the square root of 0.948 plus 0.34. That equals to 28.7. So the coefficient of drag increases as my particle size does what? So my coefficient of drag increases or decreases as with particle size? Stays the same. Notice here, okay, particle size. My particle size is increasing. So yes, as particle size decreases, coefficient of drag increases. So what do you think that's going to do to my head loss? How is head loss affected? Higher head loss, exactly. Okay, so the smaller the particle size, the higher the head loss. So we've calculated the coefficient of drag for each of the size, and you can see here, as my particle size is decreasing, you can see my coefficient of drag is increasing. So as this is decreasing, coefficient of drag is increasing. The next thing we need to do is calculate the clean water head loss. We'll actually calculate the head loss during filtration. But this is the clean water head loss. This is known as the Rose equation. There are a number of empirical equations. There is no theoretical equation. They're all empirical. Okay, that relate head loss to approach velocity, depth of the filter, porosity of the material, and the coefficient of drag and the particle size. So as we talked about, okay, as we decrease particle size, we increase head loss. If we increase the depth of the filter, what happens to head loss? It also increases. Now, if we decrease the particle size, what happens to the efficiency? It increases, exactly. Okay, so we have better quality water, but we're paying for better quality water in head loss. Depth of the filter. If we increase the depth of the filter, we increase our head loss. How does that affect efficiency? What would you expect? Deeper filter. It's, again, it increases efficiency. Exactly. So it's important to think about these factors and how they play into both the head loss and the efficiency. Okay. We can think of the same thing with the approach velocity, as you can see. Okay. And notice approach velocity is to the square. So small increases in approach velocity will have, and I'm going to put a double head loss because it's a squared term. If we increase the approach velocity, what do you think happens to the efficiency? So if we increase the approach velocity, what happens to the efficiency? It decreases. We're pushing water through quicker, so it's less opportunity to be captured. So it decreases. What we then have to do, okay, is for each of these terms here, okay, we will calculate the product of the coefficient of drag times the fraction retained. So this is 1/100. So we need the fraction retained divided by the geometric mean, and make sure that this is in meters. Okay. So we will calculate that for each of these terms here. We will then sum. So back to this equation, we have 1.067 times the approach velocity squared. I've specified a depth of 0.5 meters divided by the particle shape factor times G times the porosity, which you're told is 0.4. So times the sum of CD times the fraction divided by the geometric mean. And this is equal to 0.891 meters. Okay. This is large. We want a clean water head loss of less than 0.6 meters. So what can we do? How do we decrease this value? Okay, so this is too large. So we've gotten to this point, and this will happen. This is why you want a spreadsheet. Get to this point. Now what? Okay, so we can decrease the approach velocity. We can decrease the depth. We can pick a larger grain size. Okay, that'll give us a smaller coefficient of drag. Okay. And we've talked about the impact on efficiency of all of these factors. Okay. So in your designs, you'll need to think about this when you go through the entire design, get to this point, realize that your clean water head loss is too great, and then think about what you need to do to deal with that.